talked about two aspects. One is the nuclear has protons and the protons spin, right? Especially we talked about we being water bodies, and we almost always will be interested in having the hydrogen atoms because there is so much of H2O, right? So for every atom you have two hydrogens, so you have so many hydrogen nuclei. And so we talked about something that is spinning. Anytime something is spinning about itself, what do you have? You have angular momentum, right? So it has protons are nothing but it has mass. So when something spins, there is angular momentum to it. And of course, we also added info that these happen to be positively charged. So when positively charged particle spins, we talked about what is called as thinking like a current in a loop, and therefore there is a magnetic moment that vector that we drew yesterday. So clearly there has to be some relationship between the angular momentum and the magnetic moment that is generated, because it's the same object. This object happens to be a positively charged proton. So when you have this spinning, there should be some relationship between the angular momentum and the magnetization vector that has to be related to the material property of the object, right? So that is what we will see in the next few slides. Essentially, we are talking about angular momentum, and then you have magnetic moment. How are these two connected, right? These two are connected through the material property called as gyromagnetic ratio. And as you can see, the units, gyromagnetic ratio is nothing but radians per second per Tesla. I hope you would have heard the term Tesla. I mean, radians per second you obviously would have heard. Tesla, the capital T that you see there is Tesla, which is nothing but magnetic field strength, right? This you would have heard probably when they talk about MRI, or this scanner in this hospital is 1.5 Tesla, this is half a Tesla, this is 3 Tesla. So you would have heard this Tesla before. So essentially, of course, if you divide it by radians per second, so you could convert it to just our hertz. So divided by 2 pi, you get the more convenient notation of hertz per Tesla. What is of interest to us is there are a list of values given for different nuclei in the textbook. You can see the table. But you notice for hydrogen, the material property, what we are talking about here is the gyromagnetic ratio is 42.58 megahertz per Tesla. What this means is, if I put you in 1 Tesla scanner, the hydrogen atoms in your body, hydrogen nuclei in the body, right, has a frequency, radians per second, right, of or converted to natural hertz is 42.58. I'm hesitant to use because we'll introduce the terminology of this gyration frequency in the next slide, okay? But essentially this is a frequency of precision. And then what does this say? That means if I have a known magnet, if I have a known ability to measure the frequency, then maybe I know how I know it is hydrogen, okay? So we'll build on this material. So what we actually have is collection of identical nuclei, right? You have a sample value, sample volume that you take. You have several nuclei there, right? We are interested in hydrogen nuclei, and so all of them have different orientation that we saw yesterday, right? Each one is in different direction, so there is no net magnetization. But the moment I put that volume inside a magnetic field, right, subjected to external magnetic field, then all of the microspin starts to align with respect to the static magnetic field that is applied, okay, external magnetic field that is applied. So in the absence of external magnetic field, you don't have any net magnetization because it's all random, it all cancels each other out, right, like this. Each one is spinning in, it's at a different orientation, and therefore the net sum of all the vectors, which is the magnetization vector, is going to be 0. But we are interested in a case where we want to use it as a signal, right? And so if everything is cancelled to 0, then we actually don't really know much about. So somehow the whole scheme in magnetic resonance imaging is how do we manipulate, how do we generate these magnetic moment vectors. Of course, by virtue of having hydrogen and its own spin, there is some microscopic magnetization vector that is there. But how do we manipulate so that we get some signal out of this, right? How do we get some measurable quantity? Because random distribution, it is zero otherwise. So how do we engineer it to our advantage? That is the whole idea. So how do we do that? Is again, think about it. So we talked about analogy between the spin and the bar magnet, the spinning proton and the bar magnet. And then what we noticed is, if you take the bar magnet and put it on the table, you may have 10 pieces of bar magnets. You put them in the table and you throw that such that it is all falling in different directions initially. But then you will notice that quickly it will all align to the Earth's magnetic field. That is, when you subject this to external magnetic field, which is the Earth's magnetic field, it will all nicely align itself. Of course, you have to give some finite time, right? You throw it and then quickly it will all reorient. So what happens? Similarly, what happens if you have a spin and you have microscopic magnetic field, moment vectors? What happens to this when this is subjected to external field? You would expect similar thing, right? So let's just complete what we know of case of simple bar magnet. You throw it in any direction, right? The P naught here in this case is your Earth's magnetic field. So the bar magnet will turn to align itself. So it is experiencing a torque, and that experienced torque makes it aligned into the North Pole direction. So this has to be your resting state, which will be your low energy state. And naturally, initially when you started with, it was in a high energy state, right? So unaligned magnet experiences torque. Magnet reaches state of minimal energy. So this is the case of simple bar magnet. So now, if I ask you this question as to what do you expect your spinning charge, right? Your spinning charge which has magnetic moment, if you put it to an external magnetic field. Of course, here B naught in this diagram is Earth's magnetic field, but let's say the spin I'm putting it in I have another magnetic field and I place this spin. What is going to happen? Well, your first guess is, it's just because there is an analogy drawn, you would expect that the spinning nuclei will also align itself to the direction of the external magnetic field. And that is partially correct. I mean, it has to behave very similarly. But notice there is a big difference between the analogy of the case of bar magnet and the spinning nuclei that we use for an analogy. In case of bar magnet, the bar magnet doesn't have any angular momentum, right? Whereas in this case of spinning magnet, not only do you have spinning nucleus, not only do you have magnetic moment vector, it is similar to the effect of bar magnet, but magnetic field, but then it is having an angular momentum. So what happens when you have an angular momentum is, when it is trying to come align itself to the magnetic field, but it is spinning, that means it is having an angular momentum. I think there is one important concept that you would have heard. In fact, we use the term loosely in the previous slide, gyromagnetic ratio. So I'm sure you would have heard gyroscope, how it works. It's all brush up your third semester, fourth semester, or even first year, if depending on the college and stream that you took your undergrad. You would have had a subject called engineering mechanics, where essentially it has to do with not only force and resultant motion, but also in one of the later chapters they would have covered this precision, precision, and you have the top example. Like we'll cover some of it, but I think you should brush your material in that engineering mechanics chapter before you will be able to really get a good view of connection between the basic mechanics that is not taught at first or second semester level to how it is applied in a neat field called as magnetic resonance imaging. Okay, that is for something beyond the scope of this course, but I would urge you to go have the joy of connecting the two concepts. So essentially what we are saying here is, if you subject that magnetic moment vector to external field B in this case, then there is a dot product, which is the minimum direction, and then there is a cross product. So essentially the cross is your torque, right? So magnetic dipole therefore experiences a torque that tries to turn it in the direction of the field, right? So the interesting aspect is, unlike bar magnet, this doesn't directly come and align nicely in your external magnetic field direction that is applied, because it has angular momentum. So what happens is it behaves slightly different, and because of the angular momentum, what happens is it doesn't actually align. It is spinning around the axis, so it doesn't come and align itself, right? It is not doing this and aligning. If this is the axis, right? This is the spin. It will spin in whichever direction it was. This is the magnetic field, external magnetic field direction. You would expect the bar magnet to come like this, whereas because this is spinning, it's not going to come like that. It will try. It will go around. It will spin, but it will go around. Spinning gives its magnetic moment, but the angular momentum makes it precess around, what is called as precess around the external magnetic field direction. So since the magnetic moment is locked to spin axis, nucleus does not simply tip into the alignment of the magnetic field, but it precesses around it. Okay, so this is very analogous to the gyroscope in gravitational field. So here is an example. I mean, very nicely done animation compared to the hand that I showed. I try to use this because in a class it will be very helpful. I'll wake several of you from sleep, but the other thing is some of the concepts actually can come out very nicely when you participate. Okay, so I'll try my best to do it, pretend that you're all listening to me and try to do it. But anyway, there is animation if you want to take a look at it later. Okay, so this is called as a precession. So you would have heard this before. So what happens is, in the case of nuclear magnetization, when you put the we'll have to have some direction. So when you put the external magnetic field, let's call it as B naught cap. The bold represents that it is a vector. So it has a magnitude B naught and a direction Z. Okay, so the spins align in either of the two directions. So you have spins align in one of the two directions, and as you would have guessed, there will always be preference for low energy state. That is, in this case, low energy is considered to be the up direction. So what we are interested is not just one nuclei. I mean, you're not subjecting one nuclei alone to external magnetic field. You have a volume, right? So there are going to be many of these that are there. And so we talked about everything being random initially, and therefore the net magnetization is 0. But now you understand the concept. If you have many of them and you supply B naught, then all of them are going to try to either align in the plus or up direction or in the down direction. Of course, nature has its preference, and therefore there is a small preference towards the up. Therefore, there is more number of spins in the up direction than in the down direction, and therefore what happens? The net magnetization is always in the up direction. There is a net non-zero magnetization that is along the direction of the external magnetic field. That is the key. When you have multiple of these, right, each one, you take a volume and you have several nuclei that are spinning, you are subjecting all of that to B naught. What happens is, in the end, you have a net magnetization in the up direction. So net magnetization vector capital M is a collection of all the micro spins that are there.